Okay, let's unpack this. You hear the word algorithms just about everywhere, right? Shaping everything from or what you see online to how packages find your doorstep. But they often feel really abstract, maybe like a black box. So today, we're going to try and cut through that abstraction. We're going to deconstruct algorithms right from first principles and hopefully reveal just how profoundly they underpin our world.
Absolutely. And at its heart, really, an algorithm is, well, it's a precise set of steps, finite steps, step-by-step instructions, basically, designed to solve a very specific problem or, perform a task.
Like a recipe.
Exactly like a recipe. Think of it as the conceptual blueprint. It's the logical sequence, and it's totally abstract, language agnostic.
Yeah.
It's the pure idea behind the solution before it gets turned into code or anything runnable.
Right, the pure idea. And this blueprint thinking, it's not just for computers, is it? This precise sequential problem solving. It seems pretty fundamental to how we think, too.
Oh, completely. It has defining characteristics, right? Each step has to be unambiguous.
Right.
It needs to finish. That's the finiteness. It takes something in, an input, does something, and gives something back, an output.
And it needs to be general enough to work on different inputs, not just one specific case.
Yeah.
And effective, like actually doable.
Precisely. Think about tying your shoes. That sequence of steps, that's an algorithm. Or a navigation app, finding the best route. Algorithmic thinking is really a core human skill.
Okay, so here's where it gets really interesting for me. The relationship between that abstract algorithm, the idea, and an actual computer program. People often use those terms interchangeably.
They do, and it's a key distinction. The algorithm, again, is that abstract blueprint. The formula, totally language agnostic. A program, that's the concrete implementation. It's taking that algorithm and writing it in, say, Python or Java or C++ on.
Okay, so like the architect's drawing versus the actual house built from it.
Exactly that. The drawing has the logic, the structure. The house is the physical thing built using that logic. The program is where the algorithm lives and runs.
Got it. So how does that logic, that blueprint, actually tell the computer what to do? How does it direct the code?
Well, pretty much every algorithm, no matter how simple or complex, follows this universal pattern. Input, process, output, IPO. You give it data, that's the input.
Right.
It performs a set of instructions on that data. That's the process.
The steps.
The steps, exactly. And then it produces a result.
Simple enough. But how does it handle complexity, choices, repetition?
Well, that's where control flow comes in.
Yeah.
There are basically three fundamental structures. You've got sequential execution, just doing tasks one after another in order.
Okay.
The conditional logic, the if this, then do that, otherwise do something else. That lets it make decisions.
Makes sense.
And finally, iterative structures, loops. Repeating steps over and over, maybe until condition is met. That's incredibly powerful for processing lots of data or refining results.
And that processing power, especially with iteration, must be why algorithms are so crucial in data science, right? With the sheer amount of data we have now.
Indispensable. Absolutely critical. Algorithms automate these incredibly complex processes on massive data sets, things humans just couldn't do manually, not at that scale or speed. They turn raw, messy data into actual, actionable insights. And they do it with high precision, consistency.
And they enable predictions, right?
Exactly. Predictive capabilities are huge. They let us see patterns, make forecasts. Without algorithms, big data is mostly just noise.
Can you give us some concrete examples? Where are they making a big difference in data science?
Sure. Think about predictive analytics. Forecasting sales for a business, or a bank assessing credit risk for a loan. That's algorithms at work. Or personalized recommendations, when your streaming service suggests a movie you might like.
Yeah, sometimes spookily accurate.
Right, that's algorithms analyzing your past behavior. Also, customer segmentation, grouping customers for targeted marketing, and critical stuff like real-time fraud detection in financial transactions.
Okay, that connects directly to machine learning then. It feels like algorithms aren't just tools for ML. There's something more fundamental.
They are absolutely the bedrock of machine learning, no question. ML at its core is about computers learning from data, finding patterns, and making predictions or decisions without being explicitly programmed for every single scenario. Algorithms provide the structure, the framework for that learning process. They enable the pattern recognition, the optimization like getting better over time, and the ability to generalize to new data.
So machines learn in different ways using different algorithmic structures. What does that landscape look like?
Broadly, there are three main types, three paradigms. First is supervised learning. Here, the algorithm is trained on data that's already labeled. You give it examples of inputs and the corresponding correct output.
Like teaching it, this email is spam, this one isn't.
Exactly. So it's used for classification, like spam filters, or regression, like predicting house prices based on features like size and location.
Okay, supervised. What else?
Second, unsupervised learning. Here, the data is unlabeled. The algorithm has to find patterns and structures on its own. Think clustering, grouping similar items together without being told what the group should be, like finding different segments of customers based purely on their purchasing habits.
Interesting. And the third?
Reinforcement learning. This one's different again. The algorithm learns by doing, by interacting with an environment. It tries actions, gets feedback in the form of rewards or penalties, and learns strategies to maximize its rewards over time.
Ah, like how AI learns to play complex games or how self-driving cars learn to navigate.
Precisely. Autonomous systems often rely heavily on reinforcement learning.
Wow, okay, so you've got supervised, unsupervised reinforcement, and presumably many specific algorithms within each. How does anyone choose the right one?
Yeah, that raises a really important question. The truth is, there's no single best algorithm. It's not like there's one magic bullet. The choice depends heavily on the specific problem. Are you classifying something? Predicting a value? Finding groups?
Right.
It also depends on your data. How much do you have? Is it ladled? Is it messy? And what do you need from the output? Just accuracy. Or do you need to understand why the algorithm made a certain decision? Interpretability.
So it's more art than science sometimes.
There's definitely an element of craft to it, yes. Understand the strengths, the weaknesses, the assumptions of each algorithm. It's often an iterative process. Try one, see how it does, maybe try another. The art of algorithmic craftsmanship, you could say.
Okay, so pulling this all together, algorithms are these fundamental, precise sets of instructions. They're beneath almost all computational problem solving today. They really are the logical architecture of our digital world, enabling all this amazing automation and prediction we see.
That's a great way to put it. And what's fascinating here, I think, as these algorithms become more and more woven into the fabric of society, making decisions in finance, healthcare, even justice, understanding their principles, how they work, what their limits are, where potential biases might creep in, that stops being just a technical issue. It really becomes an ethical imperative, doesn't it, for everyone? We need to ensure they're used responsibly, beneficially.
That is a crucial point. Understanding the blueprint is key to shaping the house responsibly. A really profound thought to leave everyone with. Definitely keep pondering the algorithms, visible and invisible, that shape your world. You know, we hear that phrase all the time, right? Garbage in, garbage out. We kind of accept that data can be messy, but the sources we're diving into today, they challenge something much deeper. This idea that an algorithm is, a neutral calculator.
Right, that's the common wisdom. But what the research suggests is that these systems, they act less like judges and more like mirrors.
And they're reflecting the worst parts of our history back at us.
And amplifying them, which is the scary part.
So today we are tackling algorithmic bias. We're going to look at how these AI decisions create very real, very unfair outcomes in things like finance and justice.
But the really fascinating part, I think, is the engineering problem.
Yeah, that's what I want to get to, because according to these sources, fixing this isn't just about writing better code. It's mathematically almost a paradox.
It's a massive headache for the people building these things.
Yeah.
And it starts really early with how the systems are built. The literature calls them socio-technical failures.
Socio-technical? Okay, that sounds a little academic. What does that actually mean in practice?
It's less a bug in the code and more a bug in the world.
Yeah.
The one the code is learning from.
Okay.
So if you train a hiring AI on, say, 40 years of company records, and that company only hired men for engineering roles, the AI just learns a pattern.
It learns that male equals qualified.
Exactly. It doesn't know why. It just replicates the pattern.
So the common fix you always hear is, okay, just remove the gender column, you make the AI blind to it, and problem solved.
Yeah. And you'd think that would work. But that's where you get this illusion of neutrality. The AI just finds other things, proxy variables.
And that gets to the whole zip code issue, right?
Exactly. The AI might not see your race, but it sees your zip code. And because of decades of housing segregation, that's often a perfect stand-in for race.
Or occupation could be a proxy for gender.
Sure. The algorithm sees nurse, correlates with one outcome, programmer with another, and it rebuilds the very bias you tried to erase.
And since these are proprietary black boxes, we usually don't even know it's happening.
Not until real people get hurt or excluded.
Which brings us to finance. I mean, the stats are pretty stark. Black mortgage applicants are 80% more likely to be rejected than white applicants with similar financials. But the story that really jumped out was Crystal Marie and Eskis McDaniels.
Oh, that case is a perfect illustration. Here you have a couple with fantastic credit scores like 805 and 725 and a six-figure income. They should be ideal borrowers.
And the automated system just rejected them?
It did.
And it was because she was a contractor, right?
Yeah, the algorithm flagged her income, her gig economy income, as unstable. And here's the socio-technical part. People of color are disproportionately working in the gig economy.
So the AI wasn't explicitly programmed to be racist.
Not at all. But by penalizing that type of employment, it had the same effect. It filtered out qualified minority applicants.
It's a gatekeeper with no accountability. But being denied a loan is one thing. Being denied your freedom is another. Does this apply to criminal justice too?
It does, and the stakes are obviously so much higher. You have to look at the Compass tool.
The risk assessment tool courts use.
Yeah, to predict the likelihood someone will reoffend.
And this was the ProPublica investigation.
That's the one. They found Compass was flagging black defendants as high risk at nearly double the rate of white defendants. But the really terrifying part is the feedback loop it creates.
Explain that.
Okay, so think of predictive policing. An algorithm analyzes past arrest data and says, send more police to this neighborhood.
Huh?
So police go there, they make more arrests, and that new arrest data gets fed back into the system.
Which tells it to send even more police there.
It becomes a self-fulfilling prophecy. It justifies its own bias over and over again.
So if engineers can see this loop, why not just fix it? Tell the AI, make your error rates equal for everyone.
And that's where you run headfirst into what's called the impossibility theorem. That sounds bad.
It's a mathematical dead end. Look, you have competing goals. One is fairness, treating all groups the same. The other is accuracy, making the correct prediction.
Right.
If the underlying historical data shows different base rates for two groups, one group has been arrested more for whatever reason, you mathematically cannot satisfy all definitions of fairness and accuracy at the same time.
Hold on, so you actually have to choose. You have to pick between being accurate and being fair.
You have to make a trade-off. It's called the Pareto frontier. To make the error rates equal for black and white defendants, for example, you might have to intentionally make the model less accurate for one of those groups.
You'd have to make the model dumber to make it fairer.
In a sense, yeah. That is a brutal design choice.
So who makes that call? The government.
Well, that's the big debate. In the EU, they've taken a very cautious approach with the EU AI Act. Basically, if a system is high risk, it's either banned or heavily regulated.
And the US is more complicated. It's split. You had Biden's executive order focusing on civil rights and bias, and then Trump's order revoking it to focus on deregulation and, keeping America's tech edge. It's a real tug of war.
At least there's the NIST framework, the Map, Measure, Manage Guide. It's voluntary, but it gives companies a playbook.
It's a start. It's a push away from the black box and toward a glass box where we can at least see the trade-offs being made.
And that transparency feels so important, especially when you consider this one last thing we saw in the research. Studies show that when you give people explanations for a biased AI decision, we tend to believe it.
We rationalize it.
Yeah.
We convince ourselves the machine must know something we don't.
We trust the math more than our own gut. So that leaves us with this final thought. If the math itself forces a trade-off between fairness and accuracy, is the solution really about building better code? Or is it about refusing to let an algorithm have the final say?
That's the question we all have to answer.
Thanks for listening to The Deep Dive.